Hi everyone! Today, we embark on an exciting journey through the world of chemistry, exploring the intricate methods of separating mixtures and the foundational understanding of chemical equations. These concepts are not just academic, they are the very processes that purify our water, produce medicine, and even recycle materials to protect our planet. Let's dive into the methods of separating mixtures. Our first stop is filtration, a technique as simple as using coffee filter to separate ground coffee beans from your morning brew. It's essential for separating solid substances from liquids. Next, we have distillation, a process that could be likened to boiling seawater to capture the steam and condense it back into pure water, leaving the salt behind. It's a method that exploits the different boiling points of substances. Chromatography might sound complex, but it's something you've seen when ink spreads on wet paper, separating into various colors. It separates substances based on how they move through a medium. Evaporation takes us back to basics, using heat to turn a liquid into vapor, leaving solids behind. Think of salt, or think of salt pans under the hot sun, leaving pure salt crystals as the water evaporates. Magnetic separation is a straightforward using a magnet to pick up iron nails from a mixture of sand. It's a method that saves both time and resources in recycling and mining operations. Centrifugation spins mixtures rapidly, forcing components apart by density. It's akin to a salad spinner, but for separating blood components in medical labs. Lastly, decanting, the art of gently pouring liquid from a container, leaving solids to heavier liquids behind. It's a technique as old as winemaking itself. Switching gears to chemical equations. These are not just symbols on a page, but a language describing the transformation of reactants into products. Balancing these equations is crucial, as it adheres to the law of conservation of mass, ensuring that atoms are neither created nor destroyed. The state symbols S for solid, L for liquid, G for gas, and AQ for aqueous solutions gave us insight into the physical state of each component, allowing us to predict the conditions under which reaction occur. As we move through today's presentation, think of these methods and equations as tools in your scientific toolkit, enabling you to explore and understand the world in ways you have never imagined before. As we delve deeper into today's topics, our objectives will guide us through the practical applications and theoretical knowledge necessary to master the art and science of chemistry. Firstly, we aim to grasp and apply a variety of methods to separate mixtures, enriching our understanding and capabilities in chemical analysis and purification. Our second objective is to deduce and balance chemical equations given reactants and products. This skill is vital for predicting the outcomes of chemical reactions, understanding reaction mechanisms, and fostering a deeper appreciation for the molecular dance of chemistry. Additionally, we'll explore the application of state symbols in chemical equations. This knowledge isn't just academic, it's crucial for accurately predicting and understanding the conditions under which chemical reactions occur. Lastly, we'll engage with the observable changes that occur during transitions between solid, liquid, and gas states. Through this, we aim to connect our observations with underlying molecular behavior and energy changes, enhancing our scientific understanding and observational skills. As we journey through today's objectives, remember that each concept, each method, and each equation is a stepping stone towards a greater understanding of the world around us. Let's embrace these challenges with curiosity and enthusiasm. For in science, every question answered leads to a new questions to explore.
Filtration at its core is about separation. It leverages the principle that some materials are permeable to certain substances, but not to others. It's a method that might remind you of brewing coffee or sipping tea, where the goal is to separate the flavorful liquid from the solid grounds of leaves. Here's how it works. We start with a mixture that needs to be separated. This mixture is then introduced to a filter paper or a similar barrier, which acts as the gatekeeper between the solid components and the liquid or gas we wish to collect. The magic of filtration lies in the size of the particles. The solid particles in our mixture are too large to pass through the tiny pores of the filter paper. As a result, they get trapped on one side, much like leaves caught in a net. On the other side of the filter, we have our liquid or gas that has successfully passed through. This is what we call the filtrate. Again, this is what we call the filtrate. It's the purified component, free from the solid particles that were present in the original mixture. Imagine pouring dirty water through a sieve. The water flows through, leaving behind the leaves, twigs, and debris. That's filtration in action. Simple, effective, and incredibly useful. Filtration isn't just for making coffee or cleaning water, it's used in scientific laboratories for purifying substances, in pharmaceutical manufacturing to ensure product safety, and even in air purification systems to remove particulates from the air we breathe. Filtration is a testament to the elegance of simplicity in scientific process. By understanding and applying this method, we can separate, purify, and understand the world around us in a more detail. As we move forward, remember that sometimes the most profound solutions are the simplest ones. Transitioning from the physical separation of particles with filtration, we now delve into evaporation, a process where physics and chemistry intermingle to separate a soluble solid from a liquid. This method is as natural as the cycle of water on our planet, yet it plays a pivotal role in both nature and technology. Evaporation is a process we witness in the world around us every day, from puddles disappearing after a rain to the drying of clothes in the sun. It involves the transition of liquid into a vapor, leaving behind any dissolved solid substances. The mechanism of evaporation are straightforward yet fascinating. We begin with a mixture, perhaps salt water, which we want to separate. By heating the mixture or simply leaving it exposed to the air, we encourage the liquid component to vaporize. As the liquid turns into vapor, it leaves the scene ascending into the air. What remains? The solid that was once dissolved in the liquid now lies alone, having been left behind as the liquid evaporates. Consider the process of making sea salt. Sea salt is placed in large shallow ponds and left under the sun. Over time, the water evaporates due to the heat from the sun, and what we've left with are crystals of salt, ready to be harvested. Evaporation is not just a natural phenomenon, but a tool in our scientific toolkit. It's used in laboratories to concentrate solutions and in industries to recover valuable substances dissolved in liquids. Even the water cycle, which sustains life on Earth, depends on evaporation. In sum, evaporation is a gentle reminder of the elegance of nature's processes that science harnessed to study, separate, and utilize substances in myriad ways. As we explore further into separation techniques, appreciate the simplicity and efficiency of evaporation and enriching our understanding and application of science. As we continue our exploration of separation techniques, we encounter distillation, a process that might seem like alchemy but is grounded in the fundamental principles of physics and chemistry. Distillation allows us to separate liquids based on their boiling points, a technique invaluable to scientists and industries alike. Distillation operates on a simple premise. Different substances boil at different temperatures. Different substances boil at different temperatures. By manipulating these temperatures, we can separate substances that are mixed together. It's a method as ancient as the production of spirits and as modern as the purification of water. Let's break down the distillation process. We start with a mixture of liquids, each with distinct boiling points. We apply heat to this mixture. The component with the lower boiling point vaporizes first. The vapor rises, leaving behind the components with higher boiling point. The journey does not end here for the vapor. It travels to a cooler area where it undergoes condensation, transforming back into liquid. This liquid, now separated from the original mixture, is collected in a different container. The result is a purified form of the component that was vaporized first. Imagine a simple experiment of boiling mixture of water and alcohol. Alcohol with a lower boiling point vaporizes first as it cools and condenses. We collect pure alcohol, leaving water behind. This process is not just theoretical, but a practical application seen in laboratories and industries worldwide. Distillation is more than just a lab technique. It's crucial in the production of potable water, the refining of crude oil, and even in the creation of perfumes and spirits. It's a testament to how understanding the physical properties of substances can lead to innovative solutions for separation and purification. Distillation embodies the elegance of using physical properties to our advantage, separating and purifying substances in a manner that's both effective and efficient. As we progress in our exploration of separation techniques, let's keep in mind the versatility and utility of distillation in both the natural and industrial worlds. Moving from distillation, a technique that leverages the boiling points of liquids, we venture into the realm of chromatography, a fascinating separation technique that feels almost like a detective unraveling clues. Chromatography separates substances based on their differing affinities for a stationary phase and a mobile phase. It's process that showcases the subtle interaction between different substances and their environment. Chromatography is akin to a race where each participant, the substance, moves at a different pace depending on their interaction with the racetrack, the stationary phase, and the wind against them, the mobile phase. This race allows us to separate and identify the components of a mixture based on how quickly they move through a medium. Here's how it unfolds. We start with a mixture applied to the stationary phase, which could be a paper, gel, or another suitable material. The mobile phase, which could be a liquid solvent or a gas, then flows over through the stationary phase. The components of the mixture interact with these two phases to varying degrees. Some substances may bond more strongly with the stationary phase and move slowly, while others prefer the mobile phase and move faster. The difference in mobility creates distinct bands of spots, each representing a separate component of the original mixture. Imagine a drop of ink placed on a strip of paper, which then dipped into water. The ink, a mixture of different dyes, spreads upward with the water. Each dye moves at a different speed and forms a separate streak of color up the paper. That's chromatography in action. Simple yet profound. Chromatography is not just a laboratory exercise, it's used in forensic science for analyzing crime scene evidence, in environmental science to detect pollutants, and in pharmaceutical industry to purify drugs. This ability to separate and identify substances makes it indispensable tool in science and industry. Chromatography is a testament to the elegance of scientific separation techniques, offering us a window into a composition of complex mixtures. As we delve deeper into science, let's appreciate how techniques like chromatography equip us to see the unseen, revealing the intricate details of the world around us. As we explore the diverse techniques of separating mixtures, it's clear that science offers a toolbox brimming with methods tailored to specific needs. Beyond filtration, evaporation, distillation, and chromatography, there are other specialized techniques that harness unique principles for separation. Let's delve into a few of these methods: magnetic separation, centrifugation, and decanting, each showcasing the innovative ways we can separate materials based on their physical properties. First up, magnetic separation. This method sounds as straightforward as it is powerful. It employs magnets to separate or selectively attract and isolate magnetic materials from a mixture. Picture a stream of sand containing tiny bits of iron flowing past a magnet. The iron particles are drawn out and leaving behind purified substances or purified sand. This technique is invaluable in recycling operations, mining, and even the food industry to remove metal contaminants. Next, we have centrifugation, a method that might remind you of high-speed merry-go-round. By spinning mixtures at incredibly high speeds, centrifugation exploits the differences in the density among the mixture's components. The denser particles move outward to the bottom, while the lighter ones stay on top. This method is cornerstone in laboratory studies for separating blood components, purifying cells, and even in dairy processing to separate cream from milk. Lastly, decanting, the gentle art of separation. This method involves carefully pouring off a liquid to leave behind solids or a denser liquid. It's a technique as ancient as winemaking, where the wine is decanted to separate it from the sediment. Decanting is not just about simplicity but also about precision, allowing for the separation of liquids and solids without the need for elaborate equipment. In wrapping up our journey through the methods of separating mixtures, it's clear that the essence of these techniques lies not just in their scientific principles, but in their application to solve real world problems. From the recovery of precious metals to the purification of drinking water and the processing of food, these methods illustrate the creativity and adaptability of science in our quest to understand and manipulate the natural world. Each method, from magnetic separation to centrifugation and decanting, offers a unique lens through which we can explore materials, showcasing the diversity and innovation at the heart of scientific inquiry.
Please pause the video and answer the following questions on your graphic organizer. Let's consider, how we could separate a mixture of substance W, X, Y, and Z using physical methods. Substance W has a melting point of negative 114 degrees Celsius, boiling point of 78 degrees Celsius, and solubility in water, which is soluble. Substance X, a melting point of negative 6, boiling point of 300 degrees Celsius, and insoluble in water. For substance Y, having a melting point of 801 degrees Celsius, a boiling point of 1413 degrees Celsius, and soluble in water. And lastly, for substance Z that sublimes at 340 degrees Celsius and having the solubility in water as soluble, given these properties, here are the methods we could use to separate each substances from the mixture. Number one, filtration. This method would be most effective for initially separating substances X from W, Y, and Z, as it's insoluble in water. If the mixture were dissolved in water, X would remain as a solid residue, while others would be in the solution. Number two, simple distillation. Substance W has the lowest boiling point at 78 degrees Celsius. By heating the solution, we could boil off W and condense it back into a liquid using a condenser, separating it from the other substances in the solution. Number three, fractional distillation. If substances Y and Z were mixed, since their boiling points are significantly different, fractional distillation could be used to separate them by heating the mixture to a temperature above 340 degrees Celsius but below 1413 degrees Celsius. Z would sublime and could be condensed back into a solid, while would remain. Number four, crystallization. Since substances W and Z are soluble, they could be separated from substance Y through crystallization. Y has a much higher melting point, so by carefully controlling the temperature, W and Z could be recrystallized out of the solution. Number five, sublimation. Substance Z sublimes at 340 degrees Celsius. So by heating the mixture to its or to this temperature, Z would change directly from solid to gas without going through a liquid phase. This would allow Z to be collected separately after it resublimes into a solid upon cooling. Number six, evaporation to dryness. If the goal was to recover substances W and Z from their aqueous solution after filtration, heating the solution until all the water evaporates would have or would leave W and Z as solid residues. However, to completely separate W from Z, another method such as sublimation would need to be used afterward, considering both are soluble and have different sublimation boiling points. Each physical separation method leverages the unique physical properties of the substances, such as solubility, boiling point, and sublimation point. In a real world scenario, a combination of these methods would likely be used to achieve complete separation of the mixture into its individual components. The answers are letter A, simple distillation, letter B, filtration, letter C, sublimation, and letter D, filtration.